So this is the mechanics paper from 2022. First question's about variable displacement, acceleration, velocity, and that kind of thing. Just put in T as 2 for this question, nice and straightforward. Speed is the magnitude of this velocity, so we're going to work out the magnitude of this, which is root 12 squared plus this squared, and we'll get the answer. And then it wants us to work out the acceleration. Acceleration is dv by dt. Think of it as like a ladder. You go downwards for acceleration from velocity. So differentiate this, nice and straightforward, we just get that. When t is 4, position vector, now we integrate this for the position vector. So we go upwards, up the ladder, so we integrate this. That gets us this. Remember the plus c in vector form, because this is all in vectors, right? Now we can put in t is 4, and we know that this is this, so we can replace those things in there. T is 4 gets us this, and then we can work out C is this. We can put that back into there. And then when T is 1, we just sub T is 1 in, and we get the answer in the end. So nice, easy question to warm up. Next, we'll annotate the diagram some more. So mg comes down here. It's actually 5g because mass is 5. Therefore, we've got 5g cos theta this way, 5g sine theta this way. We can draw a quick triangle here. Tan is opposite over adjacent. So the triangle looks like this. This is the 3, 4, 5 triangle, which means sine theta is 3/5, cos theta is 4/5. So we can replace these with 3/5 and 4/5, which cancel these 5s, which is nice. So we just get that. The reaction they tell us is this. Now, this is a weird number, and it's in decimals. If you just divide that by 9.8, you get this, which is nice, and makes my diagram look neater, so I'll just do that. Resolving this force, we get a horizontal and down here. This is alpha by alternate angles. So this is x sine alpha, this is x cos alpha. We already know what sine and cos are, so we replace those. And now resolving vertically, the downward into the plane, not really vertically, but sorry, perpendicular to the plane, downwards this way is this plus this equals 7g, which means x is this. We can replace x with those things there. And then resolving horizontally, we're told this thing is in equilibrium, which means it's not sliding up or down the plane, which means the forces parallel to the plane must be equal. But right now we've got a 4g this way and a 3g this way, which means we must have an extra force, which is a friction, going this way as well, and it must be of size g, which is 9.8, I guess. And it's angled down the plane. The magnitude is now removed from x. The picture now looks like this. The resultant force is just, sorry, the reaction force is just this now, because it must be balanced with this. Friction must be going up the plane now, because the only force wants to drag this down the plane. Maximal friction force is mu times this. Mu is a half, so that just makes 2g. So F equals ma means this minus this equals mass, which is 5 times a. That makes g, divide by 5, and we have our answer. Good. Question number 3 is resultant force is just this plus this. Newton's second law says that the direction that something moves is in the same direction as the resultant force. So these two things in the same direction. There's a couple of ways you could do this. You could just write this as k 3i plus kj, or sorry, k into 3i plus j, because in the direction of means just some multiple of. And then you could set this equal to k3, and this equal to k1 or 1k or whatever. And then you could remove the k's and solve. You could also just say that this divided by 3 must equal that divided by 1, because the ratios just must be the same. And then you could cross multiply along like this, and you can end up with what they want to get. Time equals 4, we pass through this. So time equals 4, I mean, firstly, lambda is 2, so just set lambda as 2 in there, and you get mu as this, which you can then put in there and find the resultant force is this. Now, the only thing you can really do with that is F equals ma, which will get us the accelerations. That's nice, let's do that. Mass is 4, so we'll use that. We get A as this. And now where are we going with this? Well, we could just do some suvat, I think, right? Because we're looking for like a displacement. We're not really, but if we find the displacement, we can just do a Pythagoras on it to find the length. So we're looking for displacement, which is s. U is 0, because it tells us at the top here. T is 4. Half we know, A we know, we just worked it out, and T is 4. So this equation looks good, so let's use that. And this goes away, which is good. This works out to be that. And now we can do Pythagoras, like I said, on that to find the distance, and we get this as our answer. So kind of an interesting question. A bit different to normal, I guess. The moments question then here, so we've got mg coming down halfway along this rod, which is just distance A along there. We've got mg cos theta, therefore going perpendicular, just like we did on the inclined plane. Here we've got 2mg, I think, coming down, and that's 1.5a away, and therefore 2mg cos theta coming down this way. In here we've got a tension in the string, and you can see how I'm going to set up the moments here maybe, and that's 2a away because the whole thing is 2a. We've also got a reaction force over here, and that's important because we're actually on a rough horizontal ground, so there will be a frictional force acting this way of maximal force mu r, whatever mu is. And now I've put that going to the right, and the first question is, why have you put it going to the right? And the reason for that is this force is just coming down, so it has no horizontal component. This force is just coming down, has no horizontal component. This force here, though, is going this way, which means it does have a horizontal component this way. which means this is the only horizontal component we've got, and it's going to the left, which means friction must be going to the right. If it was also going left, the whole thing would just immediately slide across. So therefore, it must be going to the right. Tension of the string is t. Let's just take moments a. So we get 2a times t is the anti-clockwise turn equals a times mg cos theta plus 1.5a times 2mg cos theta. Remember, we have to use the forces that are perpendicular to the rod itself. So we end up with this. Some stuff cancels, some stuff goes together, and you end up pretty much exactly with what they wanted you to get, which is good. Given cos is this, well, we can replace that with 3/5 and we get this, so that's good. Show them this r here is equal to that. Well, let's just resolve vertically. So if we need t going vertically, now you can do a bit of angle chasing here to work out this angle. If you don't just remember that it's theta, maybe you could draw a triangle coming down here and concentrate on this triangle. There's 90 here. That makes this 90 minus theta, which means on this straight line, you've got 180 minus this 90 minus theta, which is theta, minus 90, which is just theta, and we get this angle to be theta. Again, if you wanted, you can just draw that in. Otherwise, this is definitely theta, which means this makes this cos t cos theta because it's next to the angle. And so resolving vertically, we have r plus t cos theta, all of which we know, right? T and cos theta we know, equals mg plus 2mg. And we can sort that out. That makes 3mg. This you can multiply together. This is 75 over 25, and then we take away 18, and we end up with this. Given we're in limiting equilibrium, that means friction is working as hard as possible, so this maximum frictional force is applying. So we have this equals to, well, across here is clearly going to be t sine theta, isn't it? Now, sine theta, if cos theta is 3/5, we've actually already seen this before in this paper. That means sine theta is 4/5. We already know what t is, we know what r is, we just worked it out, and we can sort this out for mu. The mg's cancel, which is kind of them, and we end up with mu as this, which cancels to this, and we have our answer. Question 5 is obviously the Suvac question. We may as well get the things out straight away. We'll set up Suvac going across and down. So upwards, if this is u here, this is u sine theta, of course, opposite the angle. This is u cos theta. So setting up Suvac going across and upwards. Across, our distance is 120, and up, our distance is 0, or a displacement, I should really be saying. U is obviously u cos theta and u sine theta in those two bits there. V I don't really care about. Acceleration horizontally is 0. Acceleration vertically is minus 9.8 because it's acceleration downwards, and I've taken upwards to be positive, I guess. And now the important thing here is that the t's are the same in both scenarios. It takes as long as it takes horizontally to get 120 across is the same amount of time it takes to get to 0 vertically. So those t's match, which is good because if I use this formula, the one without the v in it, I get this. This is nice because it goes away. And if I use this formula on these bits, so this is the formula used on this column. If I use this formula on this column, I get this. And this is great because I can rearrange this one for t. I think I get this. And then I can shove that t. It looks really painful, but I can shove that t into here, square this out, you get this. I'm going to cancel these u's. I'm going to multiply these together, and I'm going to divide both sides by 120. And I think we end up with this. You can verify that you get this number, which means you're definitely on the right tracks. If you times everything here by u squared cos squared, this just turns into a 588. This is still a 0, because 0 times anything is still 0. And this times by u squared cos squared, well, you get a u squared. Cos squared over cos is just cos, and then you have this sign, and I think we end up with what they wanted us to get. So just write that down yourself, and you'll have the answer. Maximum height is 10 above the ground. So let's modify this one here to be 10 upwards. Now, the key thing here is if we're 10 upwards above the ground, we're going horizontally only, is our velocity. So we have 0 vertical velocity at the point where we're highest. And that's really useful because what it enables us to do is to work out, if we take the equation that doesn't have t in it, which is this one, we can get an expression with u's and alphas, which is this, and then we get this, just moving this to the other side. And that's useful because now we have kind of like a simultaneous equation in alpha and u. What I chose to do was times this equation by cos both sides. And now this here is u squared cos sine sine. And u squared cos sine is 588. So I can replace that there. Divide by cos, divide by 588, we get this. Sine over cos is tan, of course. Draw yourself a little triangle. Opposite over adjacent, 1 over 3. 1 squared plus 3 squared is root 10 squared. So we get this, and therefore sine alpha is 1 over root 10, and cos alpha is 3 over root 10. I only need the sine alpha, because from here, if I square this to get 1 over 10, then I can put that in there, and I'll end up with what they want me to get. The motion of the ball is now modeled with the particle. We're going to essentially use air resistance here, and we want it to go the same distance, which of course means we're going to have to make the initial speed bigger, because air resistance adds essentially acceleration to the left. So we're going to need to make V bigger to compensate. And an extra refinement would be to stop modeling the ball as a particle and actually give it some dimensions. Thanks for watching. I'll see you next time.